look at real carefully in some of the slides, we will just point out something and move on. So this is probably one of the key things today, is learning this last reaction, which uses a word you've heard already, dehydration. With regard to alcohols, you just gave me a homework assignment that had some reactions like that. So this is a different kind of dehydration. So the one that you did look at was this, where you take an alcohol and you eliminate a water molecule from that molecule, and you get a double bond forming. You get an alkene. But what I want to show you now, and I'll use a real simple alcohol. Well, you can see from this alcohol right here, this is methanol. There's no way to make an alkene out of methanol, is there? It's only one carbon. But what could happen? Well, the methanol molecules themselves, between two methanol molecules, what do we see here? There's a water molecule. It's not a water molecule, but there's an OH and there's a hydrogen sitting over here on another molecule. And if we eliminated a water molecule from between two alcohol molecules, take a look at what would be left. We got a carbon, we got an oxygen, we got a carbon. Carbon, oxygen, carbon. And that is an ether. It's an ether. The ether functionality is this. Carbon, an oxygen sitting between two carbons, is the ether functional group. We started with methanol, and we're going to get here dimethyl ether. We just call it dimethyl ether. You can see right in the name. What kind of molecule is this? What functional group does it belong to? Ether. It's an ether. All right. Now I use that simple, I hope I'm not going too fast, but I use that simple, very simple alcohol, the simplest alcohol there is, methanol. But I want you to just see that, you can do this with any two alcohols. You could do this with ethanol. There's ethanol. There's the water molecule. We're eliminating a water molecule from between two molecules, two alcohol molecules. And we're getting an ether. So we got another ether here, but there's your carbon, oxygen, carbon. There's your ether functionality holding this molecule together. If we called that one dimethyl ether, someone want to propose a name for this one? Such a hush fell over the class. I was right in the middle. I asked this great question and a hush. Yes?
Is it diethyl ether?
Yeah. Diethyl ether. Okay? Diethyl ether. Now, okay, now what you're seeing right here, examples of simple ethers. And when we see a simple ether, we're going to try to give it a simple name. Keep it simple. And what makes them simple is that, well, you know a certain number of substituents. You know what those substituents look like, how to recognize them. And so if you see an ether that on each side of it are one of these simple substituents, then just name the two substituents. In other words, I mean, we could have this and this. Okay, they don't always need to be the same. These are all different kinds of ethers. All right, so but there's an ether. We got a carbon-oxygen-carbon bond, and we see two recognizable substituents, one on each side of the oxygen. So what are we going to call this? The only reason we're putting this di in front of here is because there's two of those. All right, so don't think that all ethers start out with the name di. They don't. This one isn't going to be di something. Name the two substituents. What are they? Ethyl, methyl, ether. Now we're getting somewhere. Okay. Yeah. Yeah, after you get a few examples, and you go, oh, okay, I see where this is going.
All right, where's the...
There's the ethyl.
Okay.
There's the methyl.
And the O is the ether.
The ether is that.
Oh.
That's the ether functionality. It is an oxygen between these two substituents. Because really, I mean, an ethyl is this.
So these will never have alkane names like methane.
I didn't say that. We didn't say that yet. Okay? We're going to get to a more complicated ether that you say, oh, that's not a substituent. That's a lot longer. And we're going to have to figure out how to name it. But I'm just saying, well, let's go to this next one. Well, let's go. Oh, that shouldn't have been the next slide. But all this slide is pointing out here is if we had something like ethanol, you could, this molecule can undergo both kinds of dehydration. You can dehydrate it there and form an alkene, or you can condense it on another molecule and get rid of a water. Like this, and you get the ether. Or you split that out and you get the alkene. So that this alcohol can do either one. What would you do? Well, there are different laboratory conditions and catalysts and different things that can drive you to the one versus the other. But both things are possible.
Question.
Yeah.
So if it's not, like, you just lost. You had me, now you lost me. So, so that first, this one, like, no, a little bit more of it, no, okay. So the HOH, why isn't it alkene? Wouldn't it be the same thing as the HHO? Or does it have to be in that?
The HOH is going to form a double bond right there. The HOH is going to form an oxygen carbon bond up there.
Okay, gotcha.
This oxygen is going to be up in there.
Gotcha now.
Maybe what I should have done here is...
So if it's going to make a double bond, it's going to make an alkene. But if it's going to make an oxygen bond, it's going to make an ethane.
So if I got this out of here... No. That's not what I want to do. What do I want to do? I want to get this out of there.
And that's going to make an ether.
Right.
Okay.
That's going to get me the ether. I'm probably trying to do too much in that drawing. Does that look better?
That looks better.
Okay.
You got it.
Okay, don't worry too much about this. Just know that alcohols can dehydrate two different ways. One forms an ether. One forms an ether. The other one forms an alkene. There are two ways of dehydrating an alcohol. One is in the molecule itself. You eliminate the water. To form an ether, you have to eliminate the water from between two molecules. I thought there was I'm missing a slide here. Where'd it go? Which slide am I thinking I'm missing?
It's just an example when you can just...
Yeah, there was a... Oh, what is it over here? No? Okay, maybe it's back here. Oh, okay, it's coming up. Sorry. Is everybody getting dizzy?
Yeah.
All right, there's two of these slides that kind of summarize the reactions. I'll skip over this one. We'll see. Well, this one may be the better one. This is what we just talked about. Alcohols can dehydrate to form an alkene. Alcohols can dehydrate to form an ether. You can oxidize alcohols, and primary and secondary and tertiary alcohols oxidize differently. Now, if you want to fill this diagram out a little bit better, you could include here, how do you prepare alcohols? An alkene plus water, or the hydration of a double bond, carbon-carbon double bond, will form an alcohol. And then if you come on over here and say, if you take an aldehyde plus hydrogen, it will give you a primary alcohol. And if you take a ketone plus hydrogenation, you get a secondary alcohol. So at the top there are three ways of preparing alcohols. And then down here are a number of different reactions of alcohols. And that would end up being a pretty good summary of Chapter 12, Reactions. All right? Okay, I think another one of these kind of slides come up, and we might just skip past it real quickly. All right, so there's a few odds and ends to pick up here. Here's one. Here is an OH on an aromatic molecule. There's our benzene. We're going to put an OH on there. And this is phenol. OL. Phenol. It's an aromatic alcohol. And don't get that confused with, let's say you had a molecule like this. What I'm showing here, this is not phenol. That is a benzene ring that is a substituent on an organic molecule. And what do we call it? How do we spell it? How do we pronounce it and spell it? What do we do when benzene is a substituent? What's it called? Got it? You're getting there.
Am I?
I don't know. I don't know. I don't know what's going on in your mind.
Word benzene.
No, it doesn't have the word benzene in it. It's not a benzyl group. It's a what?
Phenyl group.
Phenyl group. YL. So the YL on there means it's a substituent. An OL on there means it's a aromatic alcohol, an actual compound. So phenyl is not a compound. It has got to be attached to something. So that's phenyl. This is phenol. You catching my New York accent? Phenyl, phenol. All, ill. Phenyl. Gotcha. All right? Okay, now, for the exam on Monday, you should know the names of all these molecules. You should have 3x5 cards.
Bless you.
Okay? And remember, I could say draw phenol. Or I could say, what is the name of this molecule? And you'd have this structure there and it says, name this molecule. Or you'd have the name of it and say, draw this molecule. So what are the names? I'll tell you what, I should leave room here for the names, right?
Yeah, that'd be a good thing.
Quickly. Let's do this quickly. All right, what's this first one? What's that called? Cyclo what? Hexane. It's an alkane. This is the very first one we learned. Cyclohexane. This one is called what? Cyclo what? Hexene. The next one is called? What's this next one called? Benzene. And we just learned this is called phenol. And what is this one called? Well, it's got such a common name that we don't call it methylbenzene. I mean, that's an alternate name. If you Googled it, it'd say alternate name is this. But it has another name that is so common that you should call it that. Toluene. So if you're trying to guess it, you're out to lunch on this one, okay? You just got to know this one. You can't just figure these things all out because of someone's dog was named Toluene and they invented that molecule and they said, I'm going to name it after my dog. So there was an arbitrary way of naming it, okay?
And second one is at the top, in the middle.
Hex. Thank you. Thank you. Thank you. Good, Leah. Good catch. All right. So here's phenol. So like I said, make a 3x5 card of this. You don't have to make 3x5 cards of this, but just look at them. Some of these slides are just to be aware. You might have heard of this molecule, hexachlorophene. I'll go get a bottle of hexachlorophene. Oh, what is that? It's hexachlorophene. All right, there's 6 chlorines on there. Hexylresorcinol. Hexyl. I don't know why they're getting that. There's 1, 4, hexyl. Oh, that's interesting. I don't even know why it's called that, but there it is. Resorcinol must be this double OH. Here's an interesting one. We just learned these 2 things here. Here's O-phenylphenol. What's the O stand for? No, it doesn't stand for oxygen. O. The position, Trang. And what does O, what is that abbreviating? The O is abbreviating what? Remember the foot?
Oh, yeah.
Stomp. And the O is ortho. And the M is meta, and the P is para. para. So that's the orthophenylphenol.
You're so disappointed in us. You're really disappointed in us.
No, I'm not. No, I'm not.
He answered the question.
You're going to get it by Monday. All right. So there's your phenol. There's your phenol, and in the ortho position, you have a phenyl.
Okay.
That's how it's getting that name. Ortho.
About stomp? What?
Oh, I drew a little.
Did you miss that?
He drew a boo. And it's like
What day was
ST.
this? I can never remember that.
We were talking about, I don't know. I remember being
I
here.
remember. Because I was laughing at it. That's why.
Maybe
You could have a methyl here. That would be the ortho position. You could have a methyl here. It would be the meta position. And you could have a methyl here, and that would be the para position.
Okay.
And the stomp, wait, don't take a picture yet. Okay, I'm going to get out of the way. We got to quit joking around like this. They think I'm a professor here.
You're professional.
They might just say, are you going to start acting like it? Okay. Don't worry about this one.
Okay. Let's not look at this one.
Okay. Okay, now back to ethers for a minute. These slides might be a little bit out of order, but a good order would have been gone from the ethers over here now. We want to look a little bit more at naming ethers. So this one, you should look at this. I mean, you should know how to name that one right now. There's your carbon-oxygen-carbon bond. What's on either side of it? Methyls. It's called dimethyl ether. See that? I'm not disappointed in you. You're at the top of the class, okay? Yeah, we'll see. Okay, let's look a little bit at, I want to compare physical properties of ethers to alcohols. But let's look at, here's an alkane. Oh, sorry. Here, let's just think what we're looking at here. Here's an alkane, here's an alcohol. And what we are looking at are molecules that have roughly the same molecular weight. And now let's look over here and let's just round off these boiling points. Approximately 0. The alcohol, what would you round that to? 100. That's what I would round it to, 100. So the exact number, don't get bogged down in the number. We want to look at the difference, what is the contrast between the boiling point of this 60 molecular weight alcohol with this 58 molecular weight alkane. Now, we just couldn't find an alkane that was exactly 60, okay? It's close enough. A 100-degree difference. Why? There are weak interactions between alkane molecules, between these molecules. There are strong interactions between alcohol molecules. And why is that? Well, that's because if we go out to this end here, I'm going to do this quickly. If we go out to this end over here, we see a carbon, we see an oxygen, and we see a hydrogen. We got a hydrogen on an oxygen. They have very different electronegativities. So this oxygen has kind of a negative character to it, and that hydrogen has a positive character to it. So what happens over here is that you can get an oxygen, you can get hydrogen bonding between two alcohol molecules. They're like sticky. Did you ever pick up the honey in the morning, the jar of honey, and someone had left honey dripping down over the outside of it, and you go, yeah, my fingers are kind of sticky, right? These molecules are kind of sticky. They have an attraction to each other. If I get a little honey on two of my fingers are still individual fingers. I can pull them apart. Doesn't mean they're stuck together, but they are attracted to one another, and therefore it takes a lot more energy to get them to boil. Okay, now let's look at ethers. We talked about this before, but we didn't talk about ethers. We talked about the big difference between alkanes and alcohols regarding boiling points. Now here's ethers. All right? Higher boiling point, but only if you put it in percentage, 10% higher. This is 100% higher boiling point, or whatever. This has gone up 100 degrees. This has only gone up 10 degrees. So slight increase. Why? There's no hydrogen on that oxygen. There are 2 carbons. There is a slight polarity there. The oxygen still has a higher electronegativity than a carbon, but the difference isn't as great as between oxygen and hydrogen. So it's not as polar a bond. You just get a little bit of negative here and a little bit of positive over there, and you get a little bit of attraction between ether molecules, but not like between 2 alcohol molecules. That's what that slide is trying to tell you. Okay? And that's the essence of what I want you to see. Okay, now let's move on. Look at naming these 2, and let me tell you, but don't worry about both of them. Look at this one. That one has 2 recognizable substituents on either side of it. You know what that is. What is that? So now the question is, what is that?
Is it ethyl?
No, it's not an ethyl and a methyl. Isopropyl. That is an isopropyl. And I mean, if you want to think about it this way, you might see it better. All right? So that's an isopropyl group. It's not a propyl, it's an isopropyl. Propyl it would be attached to the end, but here it's attached in the middle of the 3-carbon substituent. So this is called isopropyl methyl what? Ether.
Sorry.
Ether. Okay. Okay, now Leah, what is that one on top up there? What is that?
Well,
What?
I have the answer.
What?
Yeah, because the probably has to.
Don't worry about the bottom yet. Just the top. What's on the top? Anybody? What is that group on the top? It's an ethyl. And what's the group on the bottom? Phenyl. 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 Yes. Yes. Excellent recall, what we just talked about 5 minutes ago. All right? Excellent. So now we call this ethyl phenyl ether. Yeah, there's a carbon, oxygen, carbon. There's a carbon right there. So that's all we got to have in there is a carbon, oxygen, carbon bond, and it is an ether. Yeah, there you go. There are the names. Okay, now here comes our problem. We're going to leave simple names of ethers, and I'll start dealing. See, I look over here, and I say, well, am I going to just call that a pentyl? You say, well, yeah, why don't we just call that a pentyl? You like that?
Yeah.
Okay, well, let me tell you why we can't. Because that also is a pentyl. Okay, now we're into 5 carbons, and this carbon-oxygen-carbon bond could be on the end, like it is over there. So what we got over there is this, if you just want to make the same comparison. We've got that, which is a pentyl, or 5 carbons, and an ether here. We've got 5 carbons and an ether here. And so here's what IUPAC does. It says that, okay, this thing right here, oh, come on, don't be so helpful. This thing over here is going to be called, this is a substituent, and it's going to be called a methoxy. It's a methoxy substituent. So add this to your little repertoire of substituents: methyl, ethyl, propyl, isopropyl. Now you got methoxy, phenyl, all of these. That's a methoxy group. And you can see what we're doing right here. We're going to say, okay, where is it attached? So we're finding the longest chain, pentane. And then we're saying we've got this substituent on the first carbon, and we got 1 methoxypentane. And over here we've got a methoxy. Here's our methoxy again right here, and this would be called what? 2-methoxypentane. 2-methoxypentane. What else did I want to say about this? All right, you can see the general name they're giving it is alkoxys. An alkoxy. Here's an alkyl group. It happens to be a methyl with an oxygen, so that's your simplest alkoxy, called methoxy. But we could have this situation. All right, if we're going to call that methoxy, what would we call that? Ethoxy. It's not dimethyl. Okay? Then you got an ethyl and an oxygen, ethoxy. Ethoxy. Yeah, so
you can make anything oxy as long as it has the oxygen.
yeah,
Like, show us another example.
we probably might not go. I mean, you could have propoxy. I probably won't get much more fancy there. I want you to recognize that there are alkoxy groups. Be able to handle a methoxy or an ethoxy in a name. Yeah, and that's probably good enough. All right. All right. You can slide by this slide. All this slide is telling you is that ethers will burn. As a matter of fact, they burn pretty fast. They're pretty flammable. But you have to balance them a little bit differently. When you balance them, you got to take that. But I won't give you that combustion reaction. But know that you can burn ethers. And when you do burn them, they produce carbon dioxide and water. Here is what we've already gone over, the dehydrating 2 alcohol molecules. So this is the dehydration. I probably should move these slides around a little bit. Get this in a little better order. We already covered that. Okay, just what are some recognizable ethers? 30, 40 years ago, I'm not sure if they still use that or not, but you go to a dentist and they'd say, well, we're going to put you under, and they'd put a little thing of ether over your over your mouth, and you breathe it in and you go to sleep. Ether. All right? Diethyl ether. Here is a modern day anesthetic, penthrane. Penthrane. Here's a methyl group here. Here is an ethyl group over here, but on this ethyl group there are 2 fluorines and 2 chlorines. It's giving it a certain vapor pressure. It's giving it a certain solubility in your bloodstream and affinity to your blood and your blood cells. I sat with a master's level nurse anesthetist. This is going back 4 or 5 years ago. We're sitting on a plane together, and I had this slide. I'd already been teaching this slide. I said, okay, what do you use? What do you use? We got the napkins out, and he told me all this, and he told me things like, okay, vapor pressure, solubility in the bloodstream, density of the molecule, all these things taken in consideration when they decide what thing to give. So they either give you that by vapor or by injection. Goes in, it goes into your bloodstream. It maybe binds up the red blood cells for a while, but as it comes through the lungs, it is evaporating out of the lungs. So if the doctor says, okay, I want this person to be able to walk out of the office in 1 hour, they give a certain anesthetic. I don't want this person to really feel any pain for 4 hours. They give a different anesthetic. It has a longer, you might have a lower vapor pressure, takes it longer to exhale out of your lungs. So they take molecules like this and engineer them to have the kind of properties that they need for a particular anesthetic. Okay, a lot of these slides in here are just miscellaneous things. So here's one other miscellaneous thing. What is a thiol? A thiol is an SH group on an organic compound. You're picking up the name OL like you have for alcohols, but thi is referring to the fact you don't have an OH like an alcohol. You have replaced the oxygen with a sulfur, and you have an SH. So we're taking the oxygen out of there, and we're getting a thiol. And notice where sulfur is in the periodic table. Remember, these are in these groups because of the similarities they have with one another. So oxygen binds to 2 hydrogens, sulfur binds to 2 hydrogens. You can have an OH group on a carbon, you can have an SH group on a carbon. Now that's where the similarity ends, because the SH group leads to extremely offensive odors of the molecules. Thiols are nauseatingly stinky, okay? They'll nauseate. Here's Pepe Le Pew on Valentine's Day, okay? He's heading off with his roses. He has hydroxyls. The aromas coming out of the roses are 2-phenyl ethanol. Here is geraniol, dimethyl 2,6-octadiene 1-ol, etc., which smell good. But unfortunately, Pepe Le Pew produces these kinds of molecules, these thiols. Here are the thiols. Where's the thiol on here? Oh, right there. Parts per trillion. You can detect these in the part per trillion level. So very extremely low concentrations, and we're sensitive to that. Unfortunately, if you get into that for an hour or 2 hours, you end up, they so overpower your olfactory glands that you don't smell them anymore. So if you ended up having a pet skunk, you probably think, they don't smell. Who said skunk smell?
Why would you have a pet skunk in the first?
I don't know. I don't have a pet skunk. And I don't know anybody that does. Okay. Don't worry too much about naming thiols, but if I were to say which of the following molecules is a thiol, and I had 5 molecules there, you need to hunt for a thiol. Or if I said which of the following functional groups is a thiol, or fill in the blank, a thiol is, okay? So be able to recognize and be familiar with what thiols are. We will pick this up in chapter 18. I don't want to just leave it with Pepe Le Pew. These SH groups are extremely important in proteins. This is cysteine. This is a critical amino acid in proteins and can give rise to disulfide bridges. Disulfide bridge right there between 2 of them. We will pick this up in chapter 18. But to just give you a quick little idea, if this was a protein molecule with each one of these beads being an amino acid, 2 cysteines at the right place can form a disulfide bridge, critical disulfide bridge that's needed in the structure of the protein. There's that other, this is just like the other reaction, the other summary. So we won't worry too much about this one, except that it doesn't have the dehydration to an ether. All right, we'll just leave it at that. So that slide and the one you had earlier is very similar. This slide just gives it in words. This slide shows you the reactions again. This is a reaction summary, chapter 12. And it lays out some of those. It lays them out. And those are all reactions you should be familiar with. There's the 3 oxidation reactions. There's the hydration to prepare an alcohol. Here's the hydrogenation or reduction. Remember that reduction is hydrogenation. Those are synonymous. Do you remember reduction is the addition of hydrogen or the loss of oxygen? So hydrogenation is the addition of hydrogen. So hydrogenation and reduction are synonyms, basically. And then you have the dehydration to form an alkene. You have the dehydration to form an ether. So there's a bunch of slides there looking at all these reactions a couple of different ways. And I think that's the last slide.